Hello mathematicians, physicists, and engineers, and welcome to the second lesson on solving differential equations using the Laplace transform. In this lesson, we're going to see how the Laplace transform acts on derivatives. So if we're going to be trying to solve a differential equation, we're going to have to know how the Laplace transform will act on the derivatives that compose that differential equation. Unfortunately, Laplace transform problems run very long. They can be very tedious. So I like to break it up into parts. Basically, I like to do my lessons that show the different components of those problems and have us understand the components before tackling a full problem. Now, the idea is this. The Laplace transform brings about problems that consist of three parts. The first part of those problems will be just taking the transform of the differential equation. After we take that transform, we're going to have a resulting algebraic equation, and we're going to go ahead and solve that. Now, we may be required to use techniques such as partial fraction decomposition to do so, and we'll discuss that as we go along the way. And then finally, once we get this algebraic equation in a nice format, and what I mean by nice is we want to try to get it to match up to the Laplace transform table, because we're going to use that table to go ahead and invert that algebraic equation to return the solution of the differential equation. So this is the process that we're going to be running through the next couple of lessons in this series. Let's go ahead and start by giving a theorem that shows how the Laplace transform acts on derivatives. If we're going to be applying the Laplace transform to a differential equation, we're going to need to know how the Laplace transform is going to act on those derivatives in that equation. The first one we're going to start off here is the Laplace transform of the first derivative. The Laplace transform of the first derivative is given by the Laplace transform of y prime equals s, Laplace transform of y minus y of 0. Now here, y is going to be the unknown function that we're going to be looking to find to solve the differential equation, and y of 0 will be the associated initial condition for that initial value problem. We're going to take this lesson as high as the second derivative here, and it'll say the Laplace transform of the second derivative is given by the Laplace transform of y double prime. This now equals s squared, Laplace transform of y, minus s y of 0 minus y prime of 0. Again, the y of 0 and the y prime of 0 are the associated initial conditions for the given initial value problem. Common notation, though, is to let capital Y of s equal the Laplace transform of y. So we're going to interchange the notation. Instead of using the Laplace transform of y, we're going to switch it out for capital Y of s. So we're going to express this above theorem in the following way, and this is how we're primarily going to use it throughout the remainder of this series. The Laplace transform of y prime is now s capital Y of s minus y of 0. And the Laplace transform of the second derivative will be s squared capital Y of s minus s y of 0 minus y prime of 0. All right, let's try out our first problem in this lesson. What we're going to be doing is applying the Laplace transform to an initial value problem, and then after we get the resulting algebraic equation, we'll solve for capital Y of s. So our initial value problem is y double prime minus y equals e to the t. And the initial conditions are y of 0 equals 1 and y prime of 0 equals 0. So in order to solve this, first we're going to apply the Laplace transform to both sides of the differential equation. So on the left-hand side here, I have the Laplace transform of y double prime minus y equals the Laplace transform of e to the t. All right, I'm going to go ahead and use the linearity of the Laplace transform operator. And all that means is on the left-hand side, I can just apply the Laplace transform term by term. So on the left-hand side, I have the Laplace transform of y double prime minus the Laplace transform of y. And on the right-hand side, I still have the Laplace transform of e to the t. All right, I'm going to go ahead and use those derivative formulas that I just gave to go ahead and take the Laplace transform of the derivatives on the left-hand side. So here in green, I have s squared, capital Y of s, minus s y of 0, minus y prime of 0. And that resulted from taking the Laplace transform of the second derivative. That's just the formula that we gave. And then here in blue, I have capital Y of s. Where'd that come from? That's just taking the Laplace transform of the unknown function y that we're trying to find to solve the differential equation. And on the right-hand side, the Laplace transform e to the t, that's found using the Laplace transform table with noticing that I have an a value of 1. So I'd have 1 over s minus 1. And that brings me to this stage that we're at right now. I want to go ahead and continue further working with this algebraic equation. The ultimate goal is to solve for capital Y of S. Now I want to go ahead and use the initial conditions. I want to start off first with y of 0. And we're given up here that y of 0 equals 1. So I'm essentially just going to substitute the 1 for the y of 0 at this step. And I also want to use the initial condition for the first derivative. So y prime of 0, I'm given that y prime of 0 equals 0. So I'll be plugging that in, and essentially that term is just going to disappear. Let's go ahead and take that to the next step. I'm going to show all the details here. So I'll have s squared capital Y of S minus s times 1 coming from the initial condition y of 0 equals 1 minus y prime of 0, that's the initial condition, y prime of 0 equals 0 minus capital Y of S, and once more that equals 1 over s minus 1. Let's go ahead and clean this up. So essentially what I want to do is get y of s by itself. So I'm going to collect the y of s terms first. I'll have s squared y of s minus capital Y of s minus s equals 1 over s minus 1. Now the reason I'm doing this is I want to just factor out that capital Y of s. So here's what we're going to do to finish solving this problem. I first want to add that s to both sides of this equation. And then I'm going to go ahead and factor out that capital Y of s. So let's go ahead and do that this next step. We can see here that I factored out the capital Y of s on the left hand side. It's going to leave me with s squared minus 1. On the right hand side, I have 1 over s minus 1 plus the s that I added from the previous step. Now to finish off this problem, to get y of s by itself, I'll just divide every term that we have here by s squared minus 1. That's going to go ahead and give me the answer. It's going to give me just the solution of the algebraic equation. So here we're going to have capital Y of s equals 1 over s minus 1 times s squared minus 1 plus s over s squared minus 1. Let's go for our second example now. We're going to be looking at this initial value problem, y double prime plus 2y prime plus y equals cosine of t plus sine of 2t with the initial conditions y of 0 equals 0 and y prime of 0 equals 1. Well, first, just as we did before, we're going to apply the Laplace transform to both sides of this differential equation. The left-hand side is going to have a little bit more terms than the last example, but let's go ahead and run this piece by piece using the linearity of the Laplace transform operator. So here I'll have the Laplace transform of y double prime plus that 2 is going to pull out because the Laplace transform is linear. So 2 Laplace transform of y prime plus the Laplace transform of y. On the right-hand side, I'll have the Laplace transform of cosine of t plus sine of 2t. Again, I'll be applying the Laplace transform term by term using linearity there. So let's go ahead and take the Laplace transform piece by piece here and understand each part. Here in green, I have s squared capital Y of s minus s y of 0 minus y prime of 0. That resulted from taking the Laplace transform of the second derivative. That's just the formula or the theorem that was given at the start of this lesson. Now here in orange, I still have the 2 from the previous step, and I really love to put some type of parentheses or brackets to remember to multiply that 2 in. Okay, so I have 2, and then I'll have s capital Y of s minus y of 0, and that came from taking the Laplace transform of the first derivative. Again, this is just a formula or theorem for the Laplace transform of the first derivative. And finally, here we have the Laplace transform of y, which is blue here, capital Y of s. And again, that results from taking the Laplace transform of y. The right-hand side is going to be a little tricky. We're going to be referring to the Laplace transform table here, and we're going to use it for the sine and cosine functions. So for this first piece right here, where did I get the s over s squared plus 1? Well, that's going to be the cosine formula right here. So s over s squared plus a squared. And if we look at our cosine function, my a value there is going to be a 1. So 1 squared would be 1, as I have here in the green circle. And similarly, if I look at 2 over s squared plus 4, well, that results from using the sine formula, okay? Now, in the sine formula here, a would be 2. So here I would have 2 over s squared plus 2 squared, and 2 squared would be 4. So that's how I got the right-hand side using the Laplace transform. And as we did in the previous example, I now want to clean this up. I want to start using the initial conditions that we have. So the first initial condition, this is going to be very nice, that y of 0 equals 0. So this means some terms will vanish for us. So everywhere that we see a y of 0, that's going to go to 0. So this term is going to vanish because it has a y of 0. And this term will vanish because it has a 0. All right, and let's now use the second initial condition. Y prime of 0 equals 1. And I only have one term, which is right here, that's going to use that initial condition. All right, going to the next step, let's clean this up a little bit here. So I'm going to have s squared, capital Y of s, minus the 1 from the initial condition. Distributing that 2 in there, that'll be plus 2s, capital Y of s. And then bringing down the blue Y of s, this will give me plus capital Y of s. And I went ahead and just brought down both terms from the right-hand side. Again, the goal is to solve for capital Y of s. So in the next step, we're going to go ahead and collect all the Y of s terms together. So here I have s squared, capital Y of s, plus 2s Y of s, plus Y of s, minus 1, and still bringing down the right-hand side. So where I'm going to go from here is add the 1 to both sides and go ahead and factor out the capital Y of s as we did in the previous problem. So when I factor out capital Y of s, here I'll be left with s squared plus 2s plus 1 on the left-hand side. And over here on the right-hand side, the same two terms, but I added the 1 there. And now the final step of this problem will just be dividing everything here by s squared plus 2s plus 1. And that's going to go ahead and bring me to my final result here of s over s squared plus 1 plus s squared plus 2s plus 1 plus 2 over s squared plus 4 times s squared plus 2s plus 1 and so forward. The last term here would be 1 over s squared plus 2s plus 1.